All right, let's get started. Have you ever really thought about how your computer finds one specific file out of thousands, instantly? Or how it pulls up a single contact from your phone in the blink of an eye? It honestly feels like magic, right? Well, today, we're going to pull back the curtain on one of the cleverest tricks in all of computer science. And it really all boils down to a pretty simple question.
Yeah, think about it for a sec. When you use your map app, you type in a street name, and before you can even lift your finger, boom, it's there. How in the world does it sift through millions of possibilities that fast? Is it just, checking every single street one by one at some insane lightning speed? Well, the answer to that is a hard no, not even close.
See, the real secret isn't just about raw processing power, it's all about structure. It's about organizing all that information beforehand in this brilliantly clever way so that finding what you need becomes, well, incredibly, almost unbelievably efficient. And we're going to break down exactly how it works.
So, to really appreciate just how genius this solution is, first we have to get a handle on the problem itself. I mean, what happens when you try to find something in a giant, messy, unorganized pile of information?
Just imagine trying to find a name in a phone book, but it's not alphabetized. It's just a random list. You'd have no choice, right? You'd have to start at the very first page and read every single name until you stumble upon the one you're looking for. That's what we call a linear search. And if you have a million names, you might have to make a million checks. It's awful. But if it is organized, you can just jump straight to the right section and you're done.
Okay, so what is this magical, organized structure? Well, it's something called a tree. And no, not the kind growing in your backyard, but a data structure that's just as fundamental in the world of computing. You can think of it as our own super smart, self-organizing filing cabinet. The whole concept is actually beautiful in its simplicity. You start with one single point at the top, we call that the root. And from that root, you can have branches leading to children. Now, in what's called a binary tree, the rule is that each parent or node can have at most two children, one on the left and one on the right. That's it. That's the entire basic structure. Okay, so before we get to the really cool search part, we need to understand the different ways you can walk through one of these trees. Think of them as different paths or traversals. There are three main ways to do it, and each one tells us something unique about how the data is laid out.
All right, first up is what we call pre-order. The rule here is super simple. You check in at the node you're currently on first. Then you go explore everything down the left branch. Once that's all done, you explore everything on the right. So the pattern is just check in, go left, go right.
Okay, path number 2 is in order. This time, the pattern is go left first, then check in, then go right. And when we follow that path, wait a second, look at that result down there. Do you see that? It's perfectly sorted alphabetically. That is not a coincidence, folks. That right there, that's the secret sauce. That's the key to why this is all so powerful. Remember that. And finally, we've got post order. And yeah, you can probably guess how this one works. You explore the entire left side, then the entire right side, and only at the very end do you check in at the node you started with. So it's left, right, check in. Simple as that. Okay, great. So we know how to build a tree, we know the different ways to walk through it, but how does any of this help us search faster? Well, now it's time to introduce a very special kind of tree. This is the one that makes that instant search a reality. This is it, the binary search tree, or BST for short. And it all comes down to one simple, incredibly powerful rule. For any node in the tree, everything in its left branch has to be smaller, and everything in its right branch has to be larger. That's the only rule. And that one little property organizes the entire tree automatically. And this image here shows it perfectly. Just look at the root, Alex. Every single name to the left, like Abner, comes before Alex in the alphabet, and every name to the right, like Angela, comes after. And this rule doesn't just apply to the root. It applies all the way down the tree. It is such an elegant system. And now it's time for the main event. Let's put this all together and see how this one simple rule lets us find a single piece of data in a huge tree with, and I mean this, breathtaking speed. Okay, here's our mission. We need to find the name Agnes in this tree as fast as we possibly can. Now, we are not going to check every name, we're just going to use the rule. So let's start right at the top, at the root, Alex. Step 1, we compare Agnes to Alex.
Alphabetically, Agnes comes before Alex, so it's smaller. That means we have to go left. And just like that, with one comparison, we've eliminated the entire right half of the tree. Gone. Okay, so our new spot is Abner. Let's do it again. Is Agnes smaller than Abner? Yep, it is. So we go left again, and bam! Another huge chunk of the tree is instantly discarded.
All right, now we're at Abigail. Is Agnes smaller than Abigail? No, this time Agnes is larger. So for the first time, we go right.
We've landed on Hadella. Is Agnes smaller? Yes, it is. So we take one final turn to the left and boom, there it is. Agnes. We found it. In just 4 simple steps, we navigated this entire tree and zeroed in on our target, completely ignoring almost all of the other data. That is the power of the binary search tree.
Let's put that insane efficiency into perspective. Remember that disorganized phone book? Searching 1 million names could take you, worst case, 1 million steps. That's what we call linear time. But with a balanced binary search tree, searching those same 1 million names takes, get this, only about 20 steps. 20! The search time barely goes up even when the amount of data explodes. It's not just a little bit faster, it's a fundamentally different scale of speed that's almost hard to believe.
And look, this isn't just some abstract, theoretical idea. This is the real-world technology that powers the indexing in huge databases. It's how dictionaries and phone books are built into software, and it's a huge part of how search engines can sift through the entire internet so ridiculously fast. It is literally everywhere you look.
So, the next time you do a search on your phone or computer and get a result instantly, you'll know the secret. It's not magic, it's a tree. A tree built on one incredibly simple and elegant rule. Smaller values go left, larger values go right. And it kind of makes you wonder, right? What other simple rules like that are out there, quietly powering the incredible technology we use every single day?